In this video, I'll talk about the adapter pattern, a common pattern seen in libraries, especially ones that integrate or combine other libraries. The intent of the adapter pattern is to convert one interface into another. This lets classes work together that otherwise couldn't because their interfaces aren't compatible. So in brief, an adapter allows you to program to one unified interface. And since I promised you a joke in each design pattern video, here's one about an adapter. How does Thor power his appliances? With a lightning adapter. Let's look at an example we've seen before. Shapes. The shape abstract class encapsulates the exact implementation of various types of shapes. Suppose you want to add another type of shape, a star. Drawing a star is a bit complicated, but you have a friend who already implements the class that does this, his star. But his star is not quite right. The display method is called draw. It doesn't have a location attribute, but an X and a Y attribute. And perhaps there are other smaller differences. You can't use his star class in the shape system. It doesn't implement the right methods to be a subclass of shape. What can you do? This is where the adapter pattern comes in. You create a class star that does have the right methods. And that class is a wrapper around the original his star that you'd like to use. This is how star class would be implemented. It contains a his star attribute, and it translates methods calls from what is needed by his star to what is expected by shape. Star has a display method, and that calls the draw method on his star. Because of the adapter, we can use both our original code and our friend's implementation, and we don't need to modify any existing code. We just add a new star class. Star behaves exactly the same as other shape subclasses and can be used in the system without any issues. So an adapter provides a wrapper around an existing object that needs a different interface. This allows you to fit pre-existing objects into a new structure without having to change them. Now let's take a step back. According to the GRASS principles, objects have certain responsibilities. Let's look at some more general design principles from object-oriented design, in particular encapsulation, which is the core idea of the adapter pattern. There are different ways to encapsulate parts of a system. You can use private attributes to hide data, or private methods to hide computation. You can hide one object behind another. This is what happened in the star example. You can also encapsulate types. The implementation of specific shapes, such as circles, squares, and stars, is hidden behind an abstract class shape. This is exactly what the adapter pattern achieves. Others using the shape system will only know the abstract shape class. They have no idea how the various shapes are actually implemented. This also means we can add new shapes later on without worrying about how it will impact the client's code. Therefore, we have encapsulated the implementation of shapes by using an abstract class. In the shapes example, we use inheritance to achieve what we want. But be careful with inheritance. Remember another object-oriented design practice. Favor aggregation over inheritance. Let's look at another example. Suppose I want to add a new type of circle with a special border. I could define a new subclass, special border circle, to do this. And here you see some of the drawbacks of using inheritance for this. What if other shapes also need different borders? You can't easily reuse the code in special border circle. What if you also want to add color? Should we create color subclasses for all shapes with borders? Or add borders to all shape classes with color? This leads to weak cohesion with respect to shapes, borders and colors. Now, according to the Design Patterns book, it's important to look at what is variable in your design. You want to find out what you want to be able to change without having to redesign the code. You focus on encapsulating the concept that varies. Another example. What if I need to model different kinds of animals? Each animal has several legs. Different animals have different kinds of movement: walking, flying, swimming, whatever animals do. Animals should be able to compute how long it takes to travel from a point A to a point B over a given terrain. Now, what's a good design? We can use attributes for the various properties. We add an attribute for the number of legs and for the type of movement the animal supports. But then, if you need to calculate travel time, the animal class needs to switch based on the type of movement an animal supports. If you add another movement type, you need to update this function. And what if I want to add other variations? Carnivores versus herbivores. And what about ducks? They can swim, walk, or fly. You could introduce an abstract class, animal, and add new subclasses, walking animal, flying animal, etc. But then, how do you add new variation? Carnivores versus herbivores, or cold-blooded versus warm-blooded? And what about those poor ducks? They can swim, walk, or fly. Here's a better alternative. We add a type called movement and store an attribute of that type. Then there are subclasses of movement: flying, swimming, and so on. Now, why is this better? We extracted movement out of the animal class. If we introduce new kinds of movement, we don't have to change that class. We can store speed with each movement instance so that we can make computing traveling time generic. We can introduce all kinds of properties on animals without creating complex subclasses. Overall, the code is now more robust against changing requirements. What did we actually do? We focused on what different animals have in common, a number of legs, and what distinguishes different kinds of animals, their movement. This kind of analysis is also called commonality and variability analysis, CVA. We'll talk more about CVA later on in this course. CVA is a valuable tool to have in your arsenal. You capture the common interface with an abstract class. Then, for each property that varies, use an aggregation. Subclasses can then implement the variations in those properties. As you can see, CVA takes us a step further than simple noun and verb analysis we've seen earlier. Translating CVA to software design means, with an abstract class, you need to think about the interface that is needed to handle the responsibilities of the class. Derived classes are used to implement a particular flavor or variation of the superclass. So ask yourself the following questions. How does a CVA help you think about ways that a software system can be modified? And second, is it really necessary to think about all this in the beginning of your design? If we have to think about all these things when applying design patterns, how is this still different from the waterfall model? Does this still fit with iterative software development? Agile methods focus on writing code quickly and not doing a lot of upfront design. In the next video, I'll talk more about upfront design and how design patterns fill in. If you have any questions, let me know by posting them in the Teams channel. Thanks for watching, and catch you in the next one.